In this video, we're going to be looking at a practical application of adding two vectors in which we cannot use components to add the vectors. We have to use a little trigonometry. So here's the problem. A plane's airspeed is its speed in still air. So this is the direction a plane would be going and the speed it would be going if there were no wind at all. A plane's ground speed is how fast it is actually moving with respect to the ground after wind is taken into account. So if we have some wind, in this case we have a 150 mile an hour jet stream that's blowing at an angle of 42 degrees to the plane's path, then the plane will actually be knocked off course a little bit. It'll be traveling more this direction. And if I were looking at the ground and looking at the plane and measuring its speed from the ground, that is the speed that it would appear to be going to me. Okay, so we take its airspeed, have a vector quantity that represents the plane's airspeed, a vector quantity that represents the speed of the wind. When we add them together, we get the plane's ground speed. So that's what I'm trying to find out here. What is the plane's ground speed? So I have this little diagram here, so I'm going to copy this down here. So we have airspeed. So I'm going to call this is the wind. I'm going to call this vector W for the wind, and that is 150. I don't know if I should, I think I'll just put the 150 on here. So that's my wind. Then I have the vector that is the plane's speed, which is 400, and here's the angle in between, which is 42 degrees. Now if I want to add these vectors, what I have to do is add them tip to tail. So in other words, I have to reposition the plane vector here and move it up here parallel to itself and redraw that up here. And then I could also position the wind over here if I wanted to. This probably needs to be a little longer, 150. And the actual ground speed is going to be the vector that goes right down the middle like that. And that's what I want to know, is how long that vector is. That'll tell me what the ground speed is. Now, I don't have any way of determining the components of the two vectors because all I know is that the angle between them is 42 degrees. I don't really know what either of the angles is for either of the individual vectors. So I'm not going to use components for this. I'm going to use a triangle. And I have a triangle here. I have a triangle that looks like this. Now, if only I knew one more crucial piece of information. I know this is 400. I know this is 150. I want to find this. What if I just knew that angle? Then I could use law of cosines. But it turns out I do know that angle, because if we think of this 400 vector and this 400 vector and then this wind vector, if we were to extend these lines, this is parallel lines cut by a transversal. This is 42 degrees, so this also has to be 42 degrees. So this angle right here has to be the supplement of 42, or 138 degrees. So that's 138. These two angles, these two adjacent interior angles of a parallelogram are always going to be supplements of each other. So this is 138 degrees. So that means I can, and I'm going to name this is my the resultant vector, or the result of adding two vectors. We usually call that the resultant. So this is the magnitude. We use absolute value symbols to represent the magnitude of a vector. So we can set this up as the magnitude of the vector squared is equal to 150 squared plus 400 squared minus 2 times 150 times 400 times cosine of 150. Not 150, cosine of 138. You're all screaming half point at me right now. 138 degrees. Now, if I put this whole thing in my calculator, take the square root of it, then I will have the magnitude of vector r. And I've done that on the calculator already. I think I've got it right here. It's 521.2 miles per hour. 521.2 miles per hour. Now, the second question was, by how many degrees must the pilot change the plane's bearing to stay on its original course? In other words, what is the angle between the airspeed vector and the resultant ground speed vector? So think about this. The original course of the plane was this vector right here, this 400-degree vector. The wind blew it off course, and so the new direction of the plane is this red vector. How much would the pilot have to change to get back on his original course? We'd be talking about this angle right here. So that's the angle I want to find. I'm trying to find this little angle in here. Now I know all three sides of this triangle, and I also know that that's obviously an acute angle because I only have one obtuse angle in this triangle. So I could use either law of sines or law of cosines to find that angle. And let's just do both ways. So one thing I could find, so this is part A. Part B now. Let's make that A so it's actually legible. Part B then, part B then is, I could set up as 400 squared is equal to 150 squared plus 521.2 ... squared. I would get that from my calculator in the unrounded form. Minus 2 times 150 times 521.2 ... cosine of, we don't have the name for that. Why don't we call that A? Cosine A. So we're trying to find that. So I could solve that. 400 squared minus 150 squared minus 521. Get that looking a little better. 521.2 squared. That's going to equal negative 2 times 150 times 521.2 times cosine of A. So I could divide everything by negative 2 times 150 times 521.2, get rid of all of that, and that would equal cosine of A. And then I would, to find the answer, I would take inverse cosine of all of this would equal A. And you can do multiple steps other ways, but let's go ahead and calculate that. Okay, there is my calculation. I did it all like that. Probably it might have been easier to do some simpler ones, but I got 30.89 degrees, which looks very reasonable. So we'd have to correct his course by 30.89 degrees. Now what if we did part B using law of sines? This one actually might be a little less cumbersome. So I could say sine of A over 400 is equal to sine of 138 divided by 521.2 ... So sine of A is equal to 400 sine of 138 divided by 521.2 ... And so A is equal to inverse sine of all of this. And that's really, that's actually a little bit easier, I think, to use law of sines here. You can see I got the very same answer, a little bit less typing. So I kind of prefer law of sines in this situation. And the reason I can use law of sines to find this angle is because I know the angle's obtuse. So there is the answer to that question. Now let's look at the next problem that we come along to. This one is different in that it has some different notation, and we have 3 different vectors. So if this diagram represents 3 force vectors all pulling on one central point at the origin, what vector represents the sum of the 3 forces? Now let's just kind of think through this problem. If I were to take each of these individual vectors and add them together, let me put a green one here. Remember, I can position them tip to tail. So I could take the blue vector and add it to the red vector doing that. Then I could take the green vector and add it to the blue vector. And it looks like my resultant vector is going to be going pretty much straight up like this. So that's what it looks like is supposed to happen. We'll find out if that's what does happen. Now, notice this notation. I mentioned this in the first video. This is another way of writing 7i plus 9j. So let's call the red vector vector A. So vector A is 7i plus 9j. Let me write 7i just a little better there. And vector B, which was the blue one, we'll move him back. Vector B, which was the blue one, we'll say vector B here is equal to 4i minus 7j. And vector C, we'll pull up this green here, vector C is equal to negative 11i plus 3j. And if we add them together, we get the sum of the three vectors. And we'll just call the sum the resultant vector, R, is equal to 7 plus 4 plus negative 11 is 0i. And then 9 minus 7 is 2 plus 3 plus 5j. Well, look at what we have here. 1, 2, 3, 4, 5. It looks like there is our resultant vector right there. 0i plus 5j. So if we wanted to write this as in terms of its magnitude in direction, we could say that vector R has magnitude. Why can't I spell very well today? Magnitude of 5 units, probably a magnitude of 5 units would be better, at an angle of 90 degrees. Now, I could find this really easily because it was 90 degrees. Now, if this hadn't been 0, I would have had to use the Pythagorean theorem to find its magnitude. Just reminding you of that. So there's a couple of example problems that are just a little different from what you've seen, but using components, very easy. Now, on your homework, there's going to be some problems where I'll give you 3 vectors, but you'll be given their you might be given maybe not 2 or 3 vectors, but you're given their magnitude and direction, so you have to find their components first in order to add them using components. So different pieces of information, switch back and forth figuring out what you need to know from the given information.